So afternoon, everyone. So as it was just said, I'm going to be looking into the proto-oceanic rift volcanoes in East Africa. And we pick East Africa because it has a range of rifts in the region, with the MER, or the main Ethiopian rift, being a more recent rift, where we then move into Afar, which is a more developed rift, where if it were not for a volcano in the north, it would be flooded by the Red Sea. So this produces a unique kind of ability for us to look at this, which we would not normally be able to do. So what I'm going to kind of conclude at the end of the day, I'm going to start with that, and I'm going to talk you how I came to that conclusion, is that these late stage rifting actually produce a variety of volcanism that we might not expect for things that are almost oceanic rifts. And these actually pose a giant threat to some of the poorest societies in the world. And so they really need to be a focus of some research in the future. So kind of building on from that is, why is this important? I've already said that this is a quite unique position to be able to study. And it's not only the fact that we don't normally get to study it, it's also the fact that it feeds information into the Wilson cycle. We already know quite a lot about things, but there's always more to learn. So we kind of want to look at this area and get as much as we can before it kind of further rifts. And then building on to that, what I've said with our conclusions is that we really need to look at these areas. The Sustainable Development Goals by the UN, we've recently added the fact that we need to understand these disasters, natural disasters, because they pose a threat to sustainability of the world. Aspen et al. 2011 found that 1.3 million people lived within 10 kilometers of a volcano in Ethiopia, and we still don't know much about this. And Biggs et al. In 2021 also found that the hazards associated in these areas are still completely understudied. So my objectives, to know what we're going to kind of come to these conclusions of, we need to know the typical style of volcanism in that area, okay, to be able to view these hazard maps and all the things associated. And we also need to know things like the frequency, to be able to understand the risks that are posed and how frequent these might be. And then building on from that, we need to understand what depth is this magma originating from and where's it actually being stored. Because if we understand where it's being stored, we can feed this information into things such as our seismicity and INSAR and geodesy. So once we put that all together, we actually can understand the workings and understand any signals prior to eruption. So what I have done, kind of half my thesis, is combined satellite data, so Landsat, Sentinel, Google Earth, and used GIS, particularly ArcMap, and mapped out the lava flows. Unfortunately, due to COVID and political instability, it wasn't actually able to get in the field, but we can do quite a lot from satellite. And there was a field campaign in the 1960s and 70s, which has collected a lot of samples from the area. So using that samples that are studied, that are stored, I should say, in the University of Pisa, I was able to collect some representative samples based on our map, and then carry out petrographic and geochemical analysis on these, which include major element, trace element, and isotopic, so strontium, neodymium, and lead data. And then hopefully combine all of this to give us our overview of the volcanoes. So the volcanoes I focus on were in the north of Afar, and they're called Alu, Dalafila, and Bora Ale. The reason we picked the north was it is the most rifted, it's the thinnest crust, which is about 15 kilometers thick at the area, which is much kind of closer to the oceanic crustal thickness that we're aware of. So the map that I've produced here, we can see that I've been able to split it up into 4 main stages of activity. We have stage 1, which is shown by this blue hash kind of pattern. And these are extremely high volume, covered a large area flows, and we think these are the oldest. I'm waiting on Argon dates. They're kind of taking a bit longer than expected, but they are on their way. And we see that there are some hyaloclastic textures, which shows, and we know from the past that they have been flooded previously, which is why we believe that those are that. The ages of that flooding was about 18,000 years ago, so anything since then is much younger, but the actual dates we're waiting on. We then moved further north to the area and had stage 2, which again, we have these high volume flows, but they're constrained to around Alu, which is in that top thicker black line. And we see that they are fissure dominated. So they actually tend to be sourced from around the edifices themselves on the flanks rather than the main edifice. And then even younger than that, we go on to stage 3. So these kind of yellow vertical lined areas, and this is where the volcanism changed. We see a mix of RR flows and Pahoehoe flows, so we can see that there's been a giant change in kind of composition, which we'll come on to in a little bit. And then we move back to more recent, one of which is actually erupted in 2008, which is this red flow just here. And these are lower volume, and they are again back to being fissure dominated and Pahoehoe in texture. So the compositions for the region are not what we would expect. In oceanic kind of situations, and therefore in proto-oceanic, you would be more inclined to expect that they would be basaltic in composition. But we actually find that there is a large range in compositions observed. So we can see that we actually have quite a lot of intermediate compositions and even some rhyolites. Now, these are all sourced from that yellow area, which are from the main edifices. And then the majority of the other kind of fissure-dominated systems are basaltic. So what we also found was that actually from this edifice in the south of the area, Bora Ale, was that we have pumiceous products, which imply explosive activity, which wouldn't always be kind of expected and hence pose different threats to the local regions that we need to be more aware of. So then when we move on to objective 2, so for those of you that need a quick reminder, that was to understand where the melt was originating and being stored. We've used trace element ratios and isotopes, which we'll come on to on the next slide, to understand this further. So our trace element profile, our rare earth profile on the left of the plot here, we can see that the colours correspond with the shapes. So blue circles are stage 1, green triangles are stage 2. We then jump to our stage 3, which is the yellow squares, so our more RR and more intermediate compositions, and then our red diamonds are the red. So we see that they're all very similar in composition. We have a europium anomaly, which is supported by the petrography, so in that we have plagioclase compositions. But in general, all of them seem to have this light rare earth enrichment, which is very, very different to the Red Sea compositions that have been stated previously in literature. So we believe that these are caused by different mantle sources melting compared to that of the Red Sea rift that's currently occurring. I should note as well, the black dashed line here is the Ethiopian plateau that occurred 30 million years ago, which is thought to be the onset of a mantle plume in the region. So again, it's slightly different, but there are some similarities at the end with the heavy rare earth element. So to understand where we have melting occurring, we used our trace elements to carry out modelling, and we did modelling experiments using a ratio of our our light rare earths to our middle rare earths. So actually this x-axis here is showing that, and that is implying the gradient which we see here. So the steeper the gradient, the higher the value. And then we then on the y-axis, we're showing the ratio between our middle rare earths and our heavy rare earths. So by carrying out modelling, we were able to predict what type of mantle source it was melting, whether it was spinel and garnet. Now, spinel is considered to be more stable at shallower depths compared to garnet, which is more stable at deeper depths. And the debate is about exactly what depth that kind of stability is, but it's between, people quote between about 80 and 100 kilometers is where garnet becomes stable. So the fact that we're plotting down here, or this one is zoomed in for our kind of visual aid, it shows that we are much closer to spinel than we are to garnet, but there is a small portion of garnet lertz-like melting. So what this indicates is the onset of melting is actually quite deep, but the majority of the melting is occurring much shallower. And this is reasonably consistent across all the basalts. I should note, we only looked at basalts to account for any kind of fractional crystallization effects. We took any more evolved samples out to be able to do this modelling. And then what we see is the stage 1 and 4, so our oldest and our youngest fissure basaltic volcanism is quite similar, whereas our stage 2, so that northern concentrated area, is got a slightly shallower origin, but a higher melt fraction. So we then moved on to look at isotopes to help understand where in the mantle and what our sources were for the mantle. And we actually find that it's a mixing between a Afar plume-like end member, which is a value Rooney uses a lot, which is our lead-enriched value down here in this cross here. And we believe that it's mixing with the lower crust based on this trajectory we see here. I'm aware that this is not fully sitting on the line, but that is because this is an average value, and actually it probably should be represented more by a box, which would then account for that variability. So what we see is the fact that the homogeneity, the heterogeneity, I should say, is likely caused by assimilation of the lower crust in the region and not the upper crust, which then explains more of our storage conditions when we move on to the plot on the right-hand side. Now, what this shows is our zirconium x-axis is an indicator of fractional crystallization. So the higher the zirconium, the more evolved samples. So it's similar to that TAS diagram we looked at to start with. And then what we see is our basalts, so around 200 ppm zirconium, our lead ratio is extremely heterogeneous, showing that there's a large range of crustal assimilation and potentially even this variability within this Afar plume end member. But then what we find unusually is that as we get to the evolved samples, there is a very narrow lead range. Now, this implies that there has been some homogenization of all three edifices that had the same storage. Now, what I believe is that we have a variety of basalts feeding this storage system, and then they're feeding a storage system that then homogenizes because of the mixing of them all. Hence, is about, not quite, but about midway between these basaltic ranges. And then, once this occurs, fractional crystallization progresses, allowing for this isotopic value to continue being consistent, but we get these rhyolitic and more intermediate compositions. Now, what this implies for our magma chamber system or our storage system is that we have magma feeding from depth, occurring, as we said before, starting melting at 80 kilometers to shallower. We then have lower crustal assimilation in a storage system, which previously has been measured around to be about 12 kilometers depth. And then it feeds up, and we had this homogenization of magma. And what occurs then is there is no more assimilation, it's just storage. Now, INSAR and geophysics data suggests that this is actually about 1 to 4 kilometers. So the key things that we're going to take away from this is that we have our garnet stability zone as the onset. We have our multiple magma storage zones within, so all three edifices are linked because they occur on the same lead isotopic range, and actually we have a range of compositions occurring. So we need to make sure that when we apply our hazard maps and things, we incorporate all different possibility of eruptions. So that's kind of what we're hoping to produce to feed into future research of what needs to be tackled further in the region to reduce the risk to these societies. If anyone wants to read more about my objective 1, there is a link to the paper. Paper 2 will hopefully be coming soon. So yeah, thank you.